Hey AP students, welcome back. This section, 3.3, is actually just a review of hopefully something that we already know, so hopefully we can knock this out pretty quickly. And let's do that. So what we're talking about here is we're talking about solids, liquids, and gases. So let's kind of get started. So we've got this little table we're going to fill out. Let's start with gases and we'll work all the way across. So we've got gases, their density, all right, if we think about density, it's going to be very, very low, right? Our density of a gas will be very, very low. In fact, most of the time our density of a gas is measured in grams per liter, which is actually, that's not very, it's going to be really, really small. Okay, the next one that we have there is shape. When we talk about a gas, we're talking about what shape does it have. And so its shape is variable, right? It's going to take the shape of a container. All right, its volume, same thing. It's going to be variable. It is going to take the shape of the container that it is in. Strength of intermolecular forces. We kind of hit on this in the last one when we said that gases aren't going to have very many intermolecular forces because they are not so close together. So very weak. And we're going to say that's because they are so far apart. All right, and last but not least, particulate diagrams. We actually get into this in another section, maybe 2 or 3 away, but this is good practice. A particulate diagram is something that kind of visualizes or helps us visualize what the particles would look like if we could see them. So if this box is the particulate diagram, we're just going to fill it in, and a gas would then take the shape of the container. We would have little circles everywhere, all right? And these circles, since they're all the same, or I tried to make them the same, this would be an element because they're all single, right? And they're all together, or they're all the same, all right? But we'll get into that, like I said, in another section. So let's go back and do a liquid. Density here, we could probably say medium, right? And most of the time our densities for liquids and solids is in grams per liter. And we're going to say a little bit larger here, all right? We don't know too many solids that, there's some solids that float on water, but not too many. So our shape then for a liquid is going to be variable, right? When we pour a liquid, it takes the shape of the container, right? So its volume or its shape is variable, but its volume would be fixed, right? We know its volume. Strength of intermolecular forces, well, obviously, if it's staying together as a liquid, they must be a little stronger than gases, right? But probably weaker than a solid. Okay, and then our particulate diagram, remember we say it takes the shape of a container. So this time let's use triangles, but it's taking the shape of the container here. Not super close, not tightly packed, right? But getting a little closer, right? And that's taking the shape of the container. Again, this would be an element because all the particles are the same, right? We have all triangles, so that would be an element. Maybe in the next one we'll draw a compound. Okay, so we've got our solid. Our density of our solids most of the time is high, but we do have some solids that float on water like styrofoam and some other items, but they tend to be high. And so this one, for its shape, is going to be fixed, right? The shape of a solid is fixed. When we put it in like a container, it does not take the shape of a container. Same with the volume. Its volume is also fixed. Strength of IMFs. This is going to be really, really strong. When we have a solid, it has really large IMFs. All right. And now if we draw a particulate diagram of a solid, and again, I said we would try maybe a compound, so that's 2 or more elements chemically combined. So let's take that triangle and there we go. Maybe like this. This could be our solid, and that would be a solid compound because it has the same formula and it looks the same, but it's the solid part is because it's not taking the shape of the container, it's holding its shape. All right, one last thing for this little section, and this is actually review. Allegedly, I don't know if it's review for you guys or not, but we're just going to take a quick peek at this. This is called a phase diagram. All right. AP Chemistry doesn't ask about it, but they used to, so it's also probably a little bit worthwhile. So we're going to blow this up just a little bit. So we have a phase diagram. This is of a non-hydrogen bonding molecule. That's not really that important. But what we have here is kind of, these are the three phases or states of matter. We have solid, liquid, gas. And then we can tell on these lines, based on our temperature and our pressure, where they're going to change. Like we know when between a solid and a liquid, how that's going to change. We could know what temperature that's going to be, and then what the pressure is as well. Same thing for a gas. Obviously, as we get higher temperature, right, we're more likely to be a liquid and a gas over there, right? So that is, and so you could just read it and figure it out. One key point right here, I don't know if we can see that line right there, that black dot. All right, that's called our triple point, and that's where actually all three phases of matter exist at the same time, which is kind of crazy to think about, that we could have all three phases existing at the same time, but that is something that we could do up there. This up here, this green dot, is called our critical point. All right, and what's happening in our critical point is that's where we have our liquid and our gas in our equilibrium. So we have both liquid and gas at present. But I just wanted you to see that. Not that there's going to be questions about it, but it would just be like reading a graph if you did actually see it. I might put some on a practice just so you can see, but really not super stressful. Okay, see you next time.